So this is lesson 1. First thing, we're going to check the flight controls. If I move the cursor up and down, the elevator goes down, up and down, meaning that there's a movement in the lateral axis. Moving left, right the cursor, you can see that there is a movement on the ailerons, and that causes a movement on the rolling axis, the longitudinal axis. And finally, the yaw is on the vertical axis. The yaw causes an effect on the vertical axis. Full power is applied and flaps are set to take off. And as the airplane starts rolling and gaining speed, lift is generated, and when we reach around 60 knots, we rotate and we're airborne. So if I keep my nose pointing up, my speed decreases. As we can see now on the top left corner, you can see the speed went from 68 to 62. Once we stabilize the aircraft, the airspeed can build up. And here in the air, we can check that when I move the ailerons, the cursor to one side, the ailerons affect the longitudinal, the longitudinal axis, and a roll is caused on the airplane. So now into the questions. If I move the cursor down or decrease the pitch, the elevator on the tail goes down. Forcing the airplane to come down and gain speed. If I move the cursor up, the elevator on the tail goes up. If I move my cursor left, the rudder on the tail will move to the left. If I move my cursor, to the left wing aileron will increase, or will go up, causing the left wing to move down. And if I move my cursor to right, rolling right, the left wing will go up as the aileron goes down. Then the following questions. As a pilot, if I want to go faster, I point the nose of the airplane down, as you can see now. I'm gaining speed up to 120 knots. If you're flying faster and faster, is the kinetic energy going up and down? The kinetic energy will be going up as we are exchanging gravitational potential energy, which is height, for velocity, which is kinetic energy. In terms of energy, once does your plane slow down as you climb? The plane slows down as we climb, as we are exchanging kinetic energy for gravitational potential energy, which is height. You don't touch the throttle when you climb and fly faster. If you don't touch the throttle, the plane will either stay at the same speed if you're flying stable, or decrease if you're going up. Why is it dangerous to flow slowly? Low and slowly, because if you fly slowly, there's a high chance that you might stall, and if you fly low, then you might not time to recover. And final question: if you are in a dive, going faster and faster, at some point the airspeed will stop increasing. Why? Because you will reach the maximum energy of the plane. The drag and speed will equal itself, so the plane will not be able to go faster. Thank you very much for watching, and this is the end of lesson 1. I go and see and check the weight of the aircraft. It's 296 as by the exercise. I set the weight
Then I go and make sure that I've put the data set correct for the exercise. And flaps 10, throttle all the way in. Check that it's paused, I have paused. Take the horizon, set, like a throttle the brake on. That's it's alive. I pause so I can check the data set and see the distance for the it's taken for the plane to take off. So the red line needs to be at the bottom, that red line, and that will show that the gear pressure is at 0. So here it decreases, and then eventually there it's at 0. So it took a distance of 1,397 feet, and the speed was 67 knots. Vale, no por culo. So I said stay clear and Seattle Airport. First thing I need to do is turn the engine on, because the engine is now off. So I turn the fuel pump on and then put the ignition on. Once the engine is on, I will pause so I can set the flaps and the throttle to the correct setting. So I set flaps to 10 and then I'll push the throttle all the way into full power. So once the power is set, before I forget, I'll put the weight, the new weight required by the exercise. That should be 600 pounds. There, 600 pounds. The data set and and the graph to see how long it took to take off and what speed the airplane took off with the new weight. So I check the data set parameters, so they are right, and then I want to find the point where the red line hits the bottom there, and that shows at what speed and how long it took the airplane to take off. So the distance was around 1,500 feet, and it took off at a speed of 70 knots. So first, I check the day, clear, the conditions, and the Cessna 172. Once on the runway, I check everything's fine, and I'm on course. First thing I do is I turn on the engine. Once the engine's turned on, I will check the weight that's required for this exercise. In this case, the weight required is 900 pounds. So the new weight is set 900 pounds. I will now unpause the simulator. I set the flaps for takeoff at 15 degrees. Check everything is fine, and I will increase the throttle for takeoff power. Click on the horizon to set the controls and brake off. Airspeed is live as we reach 40 knots. The airplane feels way heavier as it takes longer to accelerate. We now reach 60 knots. Slowly pull up. You can feel that the weight of the aircraft does affect the takeoff performance as it takes way longer to rotate, and the climbing performance is worse than with the other set of weights before. You can see airplanes off the ground and flying smoothly. So I pause so I can check the data from the data input. And if we carry on, you can see here, just where, seems like here is where the red line meets the bottom line there, and that has taken the aircraft around 1,800 feet, as we can see there, just 869, just under 1,900 feet, and it's taken the aircraft around, the aircraft rotated at around a speed of 71 knots, 72 nearly. So compared to the other weights, this shows that the increase of weight means an increase of takeoff distance and an increase of speed of rotation compared to the other weights. So now into the investigate questions. As the payload increases, does the takeoff distance increase or decrease?
while as the payload increases, the takeoff distance increases because it demands a higher speed and then a longer runway to take off. Does a longer takeoff distance, does a longer takeoff distance indicate more or less payload? Related to the previous question, a longer takeoff distance usually indicates more payload, as a heavier aircraft needs more speed and greater distance to generate lift. Question 3. Does the airspeed go up or down as you increase the payload? As the aircraft is heavier, it requires higher airspeed to take off, since the aircraft needs to generate more lift to compensate the extra weight. And question 4. Do larger airplanes require larger airstrips? Well, as we have proven in these videos, in the 3 videos, larger airplanes require larger airstrips because they are heavier, need a higher takeoff speed, and require more distance to become airborne safely.
So we're set 3 miles out of the airport on final, with the simulation paused and the lift arrows set from the data. We'll first do the low power stall. We'll reduce the power on the aircraft until it's 0, and then we'll slightly increase the pitch to force the airplane to stall quicker. So we're reducing the throttle. As you can see, the airplane is slowing down. We slightly pitch the aircraft up, and we maintain the angle of attack so the airplane doesn't gain speed and keeps losing speed. The airspeed now is 50 knots, and there's not much lift on the wing. That's why hence the airplane is stalling. We'll continue with the simulation. We can see how the airplane stalls, and we recover the aircraft from the stall, and the lift bars increase now. But as we were stalling, the aircraft bars were decreasing, as there was no lift generated by the wings, and the airspeed decreases as we climb. Now we'll do the high pitch stall. So as the pitch comes up, the airspeed comes down. We've gone from 80 knots to around 33. There's not much lift occurring in the wing, and as you can see, we quickly stall and we spin towards the ground, and the lift arrows pretty much disappeared. We managed to recover the aircraft, and as we increase the throttle, the airspeed increases and the lift increases as we pitch up to recover the airplane from the dive due to the stall. So we are 3 miles out from the airport now, set with the simulation paused, and with everything up, flaps and gear up. So what we'll do now is unpause the simulation, and we will first bring the gear down and see how the speed goes down as we deploy the gear, and how the drag increases due to the gear being deployed. So as we can see, the gear comes down, and we can see how quickly the airspeed is decreasing from around 130 knots we were flying at to around 111 knots ish, and we can see how the lift decreased as well due to a slower velocity due to the drag that the gear has caused. So as we put the gear back up, we can see how the airspeed slowly increases, and how the lift as well does decrease as a higher lift, higher airspeed means higher lift, as well as a less amount of drag. So next, what we do, we'll put the flaps down to see how the flaps affect drag once they're deployed. So now we are putting flaps down slowly. So we'll put first 15, then 25, and then full flap, which is around 14 degrees. And we can see the airspeed as well does decrease again from around 115 knots to around 110, around 100 knots now. But in this case, because flaps are deployed, means that lift even though that airspeed decreases, lift is maintained thanks to the increased surface area of the wing due to the flaps being extended. As well, we can see how that the drag is increased at around 111 knots ish. In newtons. And as we put the flaps back up, we can see how the airspeed increases, and as the airspeed increases, there's a higher amount of lift being generated. Thank you very much for watching, and don't forget to subscribe. So first we'll do the landing without flaps. As you can see, we're approaching the runway at around 80 knots, no flaps, and just under 2000 RPM. As you can vaguely see on the left hand side, papillae are 2 red, 2 white, and as we approach the runway, we will slowly pitch up to have a softer landing, and we will slowly reduce throttle so the plane can float, and there's a smooth touchdown into the runway. Once we hit the runway, we'll apply the brakes and reduce the throttle. The second part will be with flaps down. As you can see, flaps are set down, and we're approaching the runway from a high angle of down pitch. You can see we're approaching around 60 knots and 1500 RPM as asked by the exercise. And as we come down, you can see how the papillae are slowly turning from all full white to 2 white to red. And we will do the same as the previous landing. We will slowly pitch up as we approach the runway to reduce the rates of descent, and we can have a smooth touchdown and a smooth landing. So as we're about to hit the runway, we will slowly pull up, pitch the nose up of the airplane and reduce the throttle, and as we hit the runway, throttle off and brakes applied. Thank you very much for watching, and I hope you enjoyed it. This is lesson 6. We will first put the center of gravity at the furthest point away, further back we can, at minus 1.363. As you can see, the elevator deflection is really big due to the plane being really unstable, and a very big elevator input required, minus 1314, as you can see there. Next part, we will put the center of gravity at the most point forward we can, at 1.767, as you can see there. And you can see that the airplane is much more stable, as there's not much of an elevator deflection and not much of an elevator input required by the pilot. And as we know, the more forwards the center of gravity is, the more stable it is. Thank you very much for watching. This is lesson 7. We will first take off with a 10-foot wingspan airplane. So the first thing we'll do is set the flaps for takeoff, and then we will unpause the simulation and set the cursor for the aircraft controls. Then we will add full power and release the brakes. The plane does speed up very quickly, but due to a very low wingspan, it doesn't generate as much lift, so it will require a higher takeoff speed. So as you can see, we're still rolling at 120 knots and we're not taking off. And we slowly pull up, and we managed to take off at around, from here we can see 123 knots ish. You can see it's quite unstable takeoff due to the very short wingspan. You can see from the outside. Now we will see on the data C, you'll see that the takeoff speed was 94 knots and the takeoff distance was 1658 knots. We'll now do the same takeoff but with the 50-foot airplane. aircraft. As you can see, we'll set flaps to take off as previously done, and we will add power, full power, and release the brakes. As you can see, it takes long. The airplane just lifts off by itself without even doing any inputs. You can see we are just below 60 knots and we're still climbing, due to the high amount of lift generated by the wings. As you can see, by barely even pitching up the nose, the airplane just wants to climb by itself. The takeoff distance was 143 feet and it took the airplane rotated at 33 knots. So now we will try and land with a 10-foot aircraft. You can see it's very unstable, very hard to keep a stable approach, and we're quite low. As well, with full flaps, it's quite hard to maintain the altitude, but we managed to. But we're now slowly coming down to the runway. We'll try and release or reduce the power as we approach the runway, but due to being very unstable, it'll be very hard. We're trying to slowly approach the runway, but due to being so unstable, we just bounce off due to a very hard landing. We managed to hit the runway as on the second bounce smoothly enough for the aircraft not to bounce again, and we managed to bring it to a stop. As you can see, it's a very short wingspan, really unstable aircraft. We'll now do the second landing with a 50-foot wingspan aircraft. You can see that it's very, very stable. It's not moving around much. It's descending at a very constant speed of 80 knots. We are with full flaps as well, and you can see that we have to pitch down, force the nose of the aircraft down as it wants to climb due to the high lift being generated by the wings. We'll slowly pitch up to try and land the aircraft. Due to being such a high amount of lift being generated, the airplane just floats a lot. We're just floating a lot over the runway as we're trying to slow down to force the aircraft down. We are at around 50 knots and still the aircraft is trying to fly, and we eventually managed to hit the runway, bounce a bit as well due to such amounts of pitch deflections, trying to force the runway trying to force the aircraft into the runway. But we finally managed to bring it to a stop. Thank you very much for watching, and I hope you enjoyed it. So this is lesson 8. We will first take off with a wingspan of 15 feet. First thing we'll do is set the weight to 2,500 pounds as required by the exercise. Once that's set, we will put flaps into takeoff position. Then we will increase the power and release the brakes for takeoff. The airplane feels that it accelerates very quickly due to lower resistance as the wings are very small, and with fast approaching rotation speed. And as we try to pull, it takes a lot of effort to pull up the plane, and then it's really, really unstable. A lot of effort as well to keep the airplane airborne, as it's very unstable due to the very low wingspan, small wingspan. And then now we will check the takeoff distance. As we can see, the airplane took 1,104 feet to take off. Part 2 will be with a 30-foot wingspan aircraft. First thing we'll check as well will be the weight, and we need to set it to 2,500 as asked by the exercise. As you can see, then we will set the flaps at the same position as with the other aircraft. We'll set the flaps to position 1. We'll unpause the simulation as well, and now we will increase the power and release the brakes for takeoff. The the aircraft doesn't feel to accelerate as fast as with the last one, as there is more drag being generated by the wings, but it does take off relatively easy with not much of an effort of pulling up, and it's quite a stable aircraft, not like the one before, which took a lot of effort to pull up and a lot of effort to maintain, a lot of inputs required, not like this one, which is very stable. It took 703 feet to take off, showing how much more stable this aircraft is. And the last part, we will take off with an aircraft with a wingspan of 60 feet. As you can see, we will first set the aircraft weight to 10,000 pounds as asked by the exercise. Just a bit tricky to get the exact weight. Once the weight is set, we will, as before, set the flaps to 1. We will add power, increase the power, and release the brakes for takeoff. It is, as you can see, and it feels really a slow aircraft, as it takes a lot of effort and a lot of time to start to gain speed and accelerate due to the very high weight that the aircraft has, and as well with the massive wingspan of the aircraft, it generates a lot of drag. And with the same engine size, it takes a long time to build up enough speed to take off. So you can see there, the aircraft is very slowly building up speed. With the past two aircraft, we had already taken off by this point. It's as well tricky to maintain on the center line. The aircraft is slowly reaching 60 knots. We will try and rotate at that speed. We will gently now slowly release and start pulling up, slowly pulling up. As you can see, lots of effort and elevator input required, and it's slowly lift the nose wheel up but not the back wheels, as we are approaching 80 knots, just about, trying to keep the aircraft on the center line. And as we approach 80 knots, we will slowly now pull up again to try and take off the aircraft. And we are airborne, just slightly bouncing off the ground, and now we're finally airborne. Really hard to keep the aircraft airborne. Really not very stable aircraft, very heavy aircraft. It feels really heavy and really hard to keep airborne. We will try and keep the aircraft, but as you can see, the aircraft can't climb. It can only sustain or decrease in terms of altitude, and the takeoff distance required for this aircraft was 6,239 feet. Thank you very much for watching, and I hope you enjoyed it. So this is lesson 9. Part 1, we will be taking off with 150 horsepower. Flying with 150 horsepower. We're paused here at cruise altitude, and now we'll unpause the simulation and fly at a stable flight level and see how the aircraft behaves with 150 horsepower. You can see we're flying at around 130 knots. We will fly all aircraft with max power, so every aircraft has the same condition. So as you can see, it's quite stable. Requires very few inputs to keep the aircraft stable, and it's flying at around 124 knots. For part 2, we'll be flying with an aircraft with 300 horsepower and a very short wingspan. As you can see, it's quite unstable. As we unpause the simulation, we are still flying cruise level. You'll see we're on the yellow arch. We're flying at around 170 knots, and it does require constant input from the pilot to keep the flight level and stable. Short wingspan it causes less drag. That's why the aircraft can reach higher speeds, but it causes it to be unstable due to low lift. So part 3 we'll be flying with a 600 horsepower aircraft with a very, very big wingspan, as you can see there. As we're in pause simulation, once the plane tries to lift to go up, as with a higher power, and there's more speed. As there's more speed as well, there's more lift. We're flying at constantly at around 201 knots, around 200, 203 knots, thereabouts. You can see that it requires constant nose down input to push the aircraft down. The nose of the aircraft down. You can see we're nearly reaching the top of the yellow arc there, because we're flying around 205-10 knots ish, as we push the nose of the aircraft up to keep flight at the same flight level, as the aircraft tries to go up due to very big wingspan and the high speed of the aircraft. It has 600 horsepower. 600 horsepower as well means there's more drag, but still, that's nearly double than last time. Thank you very much for watching, and I hope you enjoyed it.